Welcome back, and this video is on interpreting kinematics graphs. We've been doing a lot with graphs, and now I'm going to try to put it all together so you see how the three different graphs are interrelated. So, moving on. First thing that we're going to look at is we have an acceleration graph here. First thing that I always do is I look over here on the vertical axis to see what type of graph I'm dealing with, because that changes how we find the information that we're looking for. So we're going to try to find the net change in velocity from 0 to 4 seconds. And that's not too bad. We use, going from acceleration to velocity, we are finding the area under the curve. So this area right here that I've highlighted, that's from 0 to 2 seconds. And then from 0 to 4 seconds, it's the area there, the highlighted area there. And what we need to do is we need to add the two areas together. Well, what we have here is we have a triangle, and the area of this triangle is 1/2 the base times the height, which is 1/2 times 2, that's the base, and the height is 1. That gives us an area of 1. And then the corresponding triangle from 2 to 4 seconds has an area of 1/2 the base, which is time, which is 2 seconds, and the height. Well, in this case, the height is -1, and that gives us an area of -1. So if we add our two areas together, we end up with a change in velocity of 0 meters per second. Okay, let's move along and see what's next. Okay, for this one, we're going to estimate the net displacement from 0 seconds to 4 seconds, or the change in position. So to go from velocity to position, we need to calculate the area under the curve. And we're going to use the area from 0 seconds to 4 seconds. Okay, so we have a triangle and we have a rectangle, so we need to find the areas of each of those pieces and add it together. So what we have here is we have a triangle that has an area of 1/2 times the base of 2 seconds times the height of 2 meters per second, and that gives us an area of 1/2 times 2 is 1 times 2 is 2 meters. And now we have a square, and it has an area of base times height. So it has an area of 2 seconds times 2 meters. And that gives us an area of 4 meters. So to cover the entire time interval of 0 to 4 seconds, we have a change in position of 6 meters. Okay, so for this sample problem, we're going to draw the velocity versus time graph from the position graph. And this really is not all that tough. What we're going to do is we're going to go segment by segment, draw the velocity graph based upon what the position graph is doing. And I'm just going to label this so it's we're talking about the same things. I guess I'm going to call that 1, 2, and this would be -1. Okay, and 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. And let's see, I'm going to make these in intervals of 2. Okay, and again, the time are going to be intervals 1, 2, 3, 4, and 5. We can see from our position graph that we have a slope of 0, which tells us that our velocity is going to be 0. Make this a little bit bolder so we can see it. So from 0 to 1 second, our velocity is 0. Now, from 1 to 2 seconds, we have a negative slope, which means our velocity is negative, and the rise is a -5 over a run of 1. So we have a -5 for the period from 1 to 2 seconds. And then between 2 and 3, the slope of our graph is 0. So we're back to having a 0 velocity during that time interval. Then from 3 to 4, we have a positive slope, meaning that our velocity is going to be positive, and we have a rise of 2.5 over a run of 1. So 2.5, a positive 2.5 is, I'm guessing right about there. So that's what our velocity graph is going to look like. And this is your multiple choice question. Go ahead and read that carefully and give it your best answer. Now, for the last part of this video, we're going to be looking at the 3 types of graphs together for a single situation, and it helps us interpret what's going on with the motion. In this case, we have a task of drawing a graphs for which the particle is stationary. So starting with the position graph, if a particle is stationary, it maintains a constant position. The slope of that position graph tells us our velocity. Well, if this has a slope of 0, that means our velocity is 0. Now, if our velocity slope is 0, that means that our acceleration is also 0. Now let's move on to the next one. We're going to draw representative graphs for a particle which has a constant, non-zero velocity. So let's take a look at something that has a constant negative velocity. I'm going to start with the velocity graph because that's what the information was for, and I'm going to give it a constant, non-zero, but negative velocity. Now the slope of my velocity graph gives me my acceleration graph, and this has a slope of 0. So our acceleration is going to be 0 again. We have a constant velocity giving us our acceleration of 0. There's no change in our velocity. Now the next graph that we need to deal with is our position graph. And our position graph tells us the slope of our velocity graph. So if I have a constant negative slope in my position graph, that's going to give me a constant negative velocity. So let's try this. I'm going to give it a constant negative slope. I'm actually even going to extend it beyond the 0 position. Those 3 graphs go together to be one representation of a particle that has a constant non-zero velocity. Now let's move on to our next set of graphs. So for this one, we have a constant non-zero acceleration. And I'm going to model a ball that we're going to throw up in the air. We're going to have it leave our hand, go up in the air, come back down, and land in our hand. The easiest place to start is to draw our constant non-zero acceleration. And since we're talking about a ball going up in the air and then falling back down, I'm going to assume that it's gravity making that happen. And I happen to know that the acceleration of gravity is usually given to be a negative number. Our acceleration has a constant negative value, which means that our velocity has a constant negative slope. And if I'm throwing the ball upwards, it slows down until it reaches the very tip, has a zero velocity at the very tippy top, and then starts falling downward, gaining negative velocity. Now that wasn't so bad. Now here's the part that's a little bit more challenging. We have to have a steep slope at 0 seconds, a zero slope at the halfway point, and a steep negative slope at the end. So I'm going to draw that here. I'm in the middle. I'm going to draw my zero slope. I'm going to just draw a little tick there. At the beginning, I have a steep positive slope, and at the end, I have a steep negative slope. And if you were to connect those points with the curve, I'm guessing you would probably draw a parabola. And that would be right. So this is what our graph looks like for an object that has a constant non-zero acceleration, and I picked a negative acceleration. Well, let's see what's next for you. Here's your free response question. Now in this case, I want you to give me a description of how the graphs would be different if the acceleration in that last example was positive. We'll see you next time.